Hello everyone, today we are going to talk about Introduction to Heat Exchangers. So the general configuration for the heat exchangers is that on one side we have fluid at T1, okay, and on the other side you have the fluid at T2, and in between you have the wall. Okay. This is the general configuration of the heat exchangers. So it can be that T1 is greater than T2, okay, or T1 is less than T2, okay. Both are possible. And also the direction of the fluid at the T1 and the direction of the fluid at T2 can be different. Say that if this one moves in that direction, fluid T2 can move in opposite direction, or it is also possible that both fluids are moving in the same direction. Okay, T1 moves at that direction, T2 moves at that direction. Okay, this is one general configuration. Or it's also possible that fluid at T1 or T2, any of it is stationary. This part is stationary, and this one moves. Okay. And the common example is that if you have a pipe, and this is the pipe, and inside the pipe fluid moves, but the environment is stationary. Okay, it doesn't move. This is the another possibility of the heat exchangers. But at the end you have a wall, and in between you have a wall, and on one side you have one fluid at T1, and on the other side you have fluid at T2. And here are examples of the heat exchangers. So one example is the condenser of your refrigerator at home. Okay, this is the condenser of your refrigerator, and inside this refrigerator condenser you have a fluid that moves. This one is called the refrigerant. There is a refrigerant here. Okay. Refrigerant moves with these tubes. Okay, it moves there and there, and you can see the turnings here. Okay, and these turnings increase the length of the travel of the fluid, and therefore it gives you better heat transfer. And this one is fluid at T1, okay, or at T2, it doesn't matter here. And you have the wall as the pipe wall, and on the other side you have the room air. Okay, and here room air is stationary, but the refrigerant moves. Okay, one fluid moves, the other one is the stationary. And you can also see here there are fins. You can see there are lots of plate fins here. There are lots of them. Okay, these fins, if you are using fin, okay, it means that there is gas. Okay? And we know that room air is gas. Therefore, we are using fin for the room air. The reason is that gases have low convective coefficient, and therefore you need to increase heat transfer area by fins. Okay. If even the heat transfer area is increased and there is no better heat transfer, then we add one more thing, that is fan. Okay. And fan increases h value because h is function of velocity. Okay. So these are the steps that we follow. If you are using gas, we are adding fins. If the fins are not enough, we are adding fan. This is one example. Another example is the heating system at our homes. So in this heating system, you have one fluid moves. This is the inlet. Okay, fluid comes in that direction, fluid comes in that direction, and this fluid moves downwards direction. Okay, you have the hot fluid, and on the one side the fluid moves in downwards direction. Okay, so this is the direction for the fluid, this is another direction. Okay, there is tube here. Okay, so you have the tube here, you have the tube here, another tube here. Okay, you have another tube here, so you can see the number of tubes. Okay, and then this one comes here and leaves the heat exchanger. Okay, and this is the one fluid. The fluid is hot. This can be at T2, and the other fluid is air, again room air, and this one is stationary. And as you notice here, and there are also fins, but these are the fins. Okay, and this is also fin. Therefore we are increasing heat transfer area by adding fins. Okay, these plates are fins. Okay, there's another example, is the car radiator, and in the car radiator you have, this one is the inlet, very similar to home radiator. So you have the inlet from the engine of the car. Okay, so this inlet is this one is, here you have the fluid. This fluid is called So this one is called antifreeze, okay, and because this one is a mixture of water and glycol, okay. Because adding glycol decreases the freezing temperature of water. For example, if it decreases at 0 degrees Celsius, adding glycol makes it negative, for example 15 degrees Celsius or 20. And also it prevents water boiling, okay. So for example, if water boils at 100 degrees Celsius, adding glycol increases it to 120, 130 degrees Celsius, okay. And you have the inlet. This is the inlet again, and there also here you have the tubes that goes the downwards direction, and then you have the outlet back to the engine, so back to the around the cylinders, okay. It rotates around the cylinders. And here also you can see there are fins. So these are the fins. So fins again, if we have added fin, it means that we have the air or any gas, okay. As we have said that if the fins are not enough, for the heat transfer rejection, then we have also fan here, okay. Then fan starts to operate, it starts to rotate and helps to increase the value of the H. Also we have the other heat exchangers. For example, in aircrafts we are using the exhaust of the aircrafts to heat the cabin, okay. So we are using this one to heat the cabin, okay. And we are using the heater core in cars, so we'll talk about this one in the next slide. And the radiators at home, we have talked about this one, a refrigerator condenser, a car radiator, and the combination boilers at our home, okay. These are all heat exchangers. Okay, this is the cooling system of the car, cooling system of car, or heating system we can call it, because sometimes we use this one to heat the cabin of the car. So what happens is that here you have the water glycol mixture, okay. The cylinders are hot. These are hot cylinders. You have 4 hot cylinders, okay. And what happens is that when the water glycol mixture here gets the very high temperature values, for example 80 degrees Celsius, and then this thermostat is released, okay. So released, and then this glycol mixture that is around the engine cylinders travels in that direction, and then that direction, and then to this radiator. We have said that in this radiator it goes the downwards direction and back to this lower tank, okay. These are radiator tanks. So this one is upper tank and this one is the lower tank, okay. Then from this lower tank it goes back to the cylinders, and the cooling process or heat exchanger happens here. So you have the fins to help the heat exchanger, and you have the fan here. And as we have said, if the fins are not enough, the temperature increases to higher values, for example at 90 degrees Celsius. When the temperature is 90 degrees Celsius, the fan starts, okay, because the cooling system by the fins is not enough, okay. And then the fan starts and it helps to decrease the temperature of the radiator, okay. So this one is the airflow direction. This one is the airflow direction, okay. It decreases the temperature of the glycol water mixture, okay. And as you can see, these are all connected to engine crankshaft, okay. So they are connected with the same belt. And also here you have another valve here. So this one is the valve, okay. And since this glycol water mixture is very hot, so what happens is that then this mixture is diverted to another tube here. So this one is the tube here, you can see the tube, okay. And here you see there is again fins, okay. And here you have fins because we are blowing. So here you have the blower, we are blowing air, okay, into the cabin, okay. So they are using heat the cabin, okay. And the fins because you are blowing the air into the cabin of the car using the same mixture here. Okay, this is the cooling system of the car, and this is how it works. So we have one heat exchanger here, and we have another heat exchanger here. So now comes the next part, And the next part we are talking about the classification of the heat exchangers. So there are different classifications, but we will use the simplest one to understand how they work. So the first classification is that the direction of the flow, if it is co-flow or parallel flow, it's also called, or if they are flowing in opposite direction, it's also called the counterflow. Co-flow means both fluids, hot and the cold fluid, are moving in the same direction. Counterflow means the one moves in that direction, the other one moves in the opposite direction. Okay, and there is a one famous example here that we have. So this one is the counterflow heat exchanger. So what happens is that one part is the artery, another one is the vein. Okay, so you can see that the vein is blue and the artery is red. You can see the artery here and the vein is around the artery. So in artery, blood moves in that direction, okay, and in veins, blood moves in opposite direction. Okay, this one is the counterflow heat exchanger, because this artery is hot blood because it comes from the heart, and the vein is the cold blood, and because it goes from the body because it has lost its heat. And during that process, we are heating the cold blood, which goes by the artery, which goes by the veins. Okay, and therefore we are helping the work of the heart. Okay, and the same, you can see the process here. So we have the artery, which moves, blood moves in that direction, and the veins, blood moves in opposite direction, and by this process we have the counterflow heat exchanger and how it works. Okay, so and also the counterflow heat exchangers has the highest efficiency. Okay, highest, let's say, effectiveness. Another one is the cross-flow heat exchangers. Cross-flow heat exchanger is that you have two fluids moving at the same time but in cross-flow direction. So one moves in that direction, the other one is crossing it, okay, across it, the heat exchanger. So we have two types of it. So one is that both fluids are unmixed. Unmixed means that, say that this one is the fluid that moves, okay. So if I put a plate here, if I put another plate here, so plate 1 and the plate 2, okay, then it is called unmixed fluid, because by adding plate I am unmixing the fluid here. There is no unmixing in real life. With ideal case we say that it is unmixed. Okay? So we are unmixing the fluids here. So same happens here. You have the plate here, you have another plate, you have another plate. So the fluid is unmixed. So this one is unmixed. And also the fluid that you have in the tubes, you can see the fluid in tubes, they are also unmixed because they are moving in different tubes. Okay, this one is also unmixed. So in this case, both fluids are unmixed. The other one is that one fluid is unmixed. You can see here, so the fluids in tubes, these are unmixed because they are moving in different tubes. As you notice a similarity here, we have the fluid plates in between, and this is unmixed. But this fluid is mixed, okay, because there are no any plates or there are no any barriers that prevents its mixing. Okay, therefore this one is called mixing. This is the name. Okay, the other one is called the unmixed. So we have the one fluid mixed, the other fluid is unmixed case, which is the A. This is called the cross-flow heat exchanger. Cross-flow heat exchanger has effectiveness just less than counterflow heat exchanger. Okay, so maximum effectiveness is counterflow and then cross-flow. The next heat exchangers can be grouped as shell and the tube heat exchangers. For the shell and the tube heat exchanger, we have the tubes here. So these are the tubes. This here, these are the tubes here. These are the tube, and around the tube we have the shell. Okay, this body is called the shell. Okay, and this one is called the tube. Okay. And these tubes together, so we have three tubes here. It is called the tube bundle. Okay, so tube bundle means these tubes all together are called the tube bundle, and the shell is around it, and here we have the baffle. Okay, so baffle. So what happens is that if this one is the inlet of the shell part, and this one is the outlet of the shell, so outlet for shell. Okay. And the other one is the inlet for the tube. So this one is the inlet for the tube, and this one is the outlet for the tube. What happens is that the shell part, due to addition of the baffles, they are moving in this manner. Okay. So what happens is that by adding baffles, okay, you are increasing residence time. Increase residence time. Okay, as you increase the residence time, it means that increased heat transfer. Okay, by increasing the time, you have a better heat transfer. Okay, therefore we are using the baffles in this heat exchanger. Okay, there is another classification for the shell and the tube heat exchanger, is that we could have two tube passes but one shell pass. It means that you have one tube pass and you have another tube pass here. You have the U-turn here, this one is U-turn, and this one is called two tube passes, one shell pass, because there is only one shell. The other case is that two tube passes and the four tube passes and the two shell pass. And here you can see there is one tube pass, there is another one, and there is another tube pass, and there is another tube pass. You can see 1, 2, 3, 4 tube passes. So this can be the inlet and this can be the outlet. But for the shells we have two shell passes. So this one, if this is the inlet of the shell, okay, and you could have the baffles here, so there can be the baffles, something like this one. So the fluid moves in that direction, okay, and then if there is baffle one more time, this is the first shell, and then comes the next shell. The fluid comes here, again it moves in that direction, okay, then leaves the shell. So you have two shell passes, 1, 2, and the 4 tube passes, which is 1, 2, 3, 4. And there is an animation here, it shows clearly how the shell part moves and how the tube part moves, okay. And this one is the inlet for the tube. You can see the inlet and the tube. So there are lots of tubes here, so these are, again I said, tube bundle. So you have the tube bundle here. We have two tube passes here, so this one is the one tube pass and this one is the another tube pass, okay. And we have also one shell pass here. Here we have two tube passes, but one shell pass. It moves in that direction, okay. So again it follows a zigzag way due to addition of the baffles here. It moves in that direction, okay. And this one is the outlet for the tubes, so this one is outlet for the tubes, and this one is the outlet for the shell, okay. Okay, these are also baffles. And we have also other types of the heat exchangers. Here you can see we have the tubes here, these are the tubes. And again you can see there are lots of fins here, so fins. Again we are using fins if we have the gas. So it means that these heat exchangers will be used for the gas fluid in one side. Another type of heat exchanger is that plate heat exchangers. And plate exchangers means that you have lots of plates, so you can see the plates, this one is 1, this one is 2, 3, 4, there are lots of plates, but they are packed together, okay. So these are also called the compact heat exchangers, so we will talk about what is compact heat exchanger. These plate exchangers, you can see here that the same plate exchanger shown in simple form. So this one is the cold fluid, you can see the cold fluid moves in that direction. Then it follows firstly the first plate, okay, and then the third plate and the last plate. And we have at the same time hot fluid, and it moves in opposite direction the cold fluid, and it follows the alternating plates. Okay, if it moves in that plate, it moves in next plate for the hot fluid, and next plate is cold and then hot. So they are stacked together, and therefore you have good heat exchanger between these hot and the cold fluids. And then we have one more heat exchanger, which is famous for ventilation systems. Okay. And these are called heat recovery, because you are recovering the heat of the room and these are also thermal wheels, rotary heat exchanger, rotary air to wheel heat exchanger, or heat recovery wheel. So what it means is that this one is the room air, so hot room air, it moves in that direction, and then you have cold air from environment, cold air from environment. What happens is that, so this hot air that leaves the room heats one part of this wheel. Okay, this part of the wheel becomes hot. Okay, this part is hot, and you can see here there are lots of fins here. So if you look at the top view of this heat exchanger, then you can see that there are lots of fins here. So I show the cross-sectional view of this heat exchanger, and there are fins here, and lots of heat exchangers fins here. Okay, so these fins, these are also called the matrix. Okay. They help to increase, because here you have the gases in both sides, they help to increase heat transfer, as we have talked about in our first slides. Okay, so then this part becomes very hot. As the wheel rotates, okay, when it rotates, this hot part comes in contact with the cold part, okay, cold air from the environment. Then this cold air from environment gets the heatness, gets the heat. Then this cold air from the environment gets the heat of the hot air that leaves the room, and then this one becomes hot here. Okay. As you notice here, we are not using the heat exchange between this hot air and the cold air, but we are using a third material. Okay. And we are using third material, which is this matrix or the wheel here. So this is very similar to our breathing system. Okay. Okay, so breathing system, say in winter, okay, say in winter. So in winter, when you breathe in, so let me show you, if this is your throat, okay. So when you breathe out, the hot air that leaves your lungs, okay, so this hot air leaves your lungs, then heats this throat, okay, so this one gives off its heat to the throat, okay, then this throat becomes hot, and when you breathe in the cold air from the ambient, so that you get the cold air, breathe in, then this cold air from the environment gets the heat from the throat. Yeah, again, you can notice here the hot air and the cold air, they are not confronting each other, but hot air gives heat to the throat, and then cold air gets heat from the throat. We are using the third material, which is the throat here, which is very similar to matrix here. Okay, and one last part is the cooling towers in heat exchangers, and also we have the compact heat exchangers. Cooling towers, so these are used in power plants as well as in HVAC systems, or heating, ventilation, air conditioning systems. What happens is that one side, this part is the hot water that leaves the plant or the turbine, and in opposite side you have the cold air, okay, by fan. Okay. This cold air and the hot water, so when they are coming in contact with each other, then hot water gives off its heat to the cold air, and this process, and you can see the clouds here. These clouds are due to condensation of the cold air. And the similar cooling tower is in HVAC systems, and you can see the fans here. There are fans, and you have on one side you have the hot water, and on the hot refrigerant or water, it depends, and on the other side you have the cold air, and when they are coming in contact you are losing the heat. And this heat exchanger, cooling tower heat exchanger. And the last part is the compact heat exchangers. Compact heat exchangers is that when you have the surface area for the heat exchanger per unit volume, if it is greater than 700, it is called the compact heat exchanger. Okay. You can see here you have one volume here. This is the volume of the heat exchanger. This one is the volume of the heat exchanger. When you find the volume of this heat exchanger, and you have to find also the surface area of these fins, there are lots of fins here, and you find the surface area of the fins, and you have to find the volume of the heat exchanger. If this ratio is greater than 700, it's called compact heat exchanger. So one example could be the radiator. Okay, radiator of your car has a, this is called area density. Okay, radiator of your car has an area density of 1000. Yes, another one can be, the famous one is our lungs, and it has a surface area to volume which is 20,000. Okay. These are the common heat exchangers that are used in industry. Okay. And next lecture we will be the analysis of the heat exchangers, and then we will do examples about it. Now we are going to analyze heat exchangers and how to solve heat exchanger problems. Okay, so first we will start with overall heat transfer coefficient. Overall heat transfer coefficient. Okay, it is also shown as U. Okay, what is overall heat transfer coefficient? And then we will analyze. We will try to understand how to solve heat transfer problems. Okay, we have a simple heat exchanger here. So these are called the tubular heat exchanger. Okay. Or concentric cylinder heat exchanger. In one tube, so you can see there are two tubes here, tube 1 and tube 2. In one part you have one fluid. This one is fluid 1 for the one tube, and in the annular space here you have fluid 2. They can move in same direction or they can move in opposite direction. Similarly here, the same heat exchanger but in different view, and then you have fluid 2. And this is the cross-sectional view of the same heat exchanger, and here you have fluid 1, and the annular space here you have the fluid 2. And we will try to get the picture of the resistance network between this fluid 1 and the fluid 2. For that resistance network, first we should get the familiar with the fouling resistance. So this one is fouling resistance. Fouling resistance means that after some time in the pipe walls, inside the pipe wall, you have the dirt or the contaminants. Okay. This dirt or contaminants creates resistance between fluid here and the fluid outside of the tube. If you go back to here, if you have the contaminants here, okay, these contaminants creates resistance between fluid 1 and the fluid 2. And in other words, it breaks thermal communication between these two fluids. It is also possible that you have the contaminants on the outer wall of the inner tube. Okay. And these are called the fouling resistance. These fouling resistance are shown in the table as fouling factor. Okay. Fouling factor in tables. Okay, you can look for the tables, and these are all experimental. Okay, experimental. You can look fouling factor in tables, but in tables they are given as for 1 meter square. Okay, it is very similar to thermal contact resistance. Okay, what you will do is that you will divide, so to get the fouling resistance you should divide the fouling factor by the surface area. Okay, this one is the fouling factor. Okay. And it is very similar to thermal resistance. To find the thermal contact resistance, what we were doing is that we were dividing the contact resistance in the tables by the cross-sectional area. Okay, they are very similar here. We are dividing the fouling factor in the tables by the surface area, similar to contact resistance by the cross-sectional area. So if I write the if I write the thermal resistance network between fluid 1 and the fluid 2, let's say that fluid 1 is at temperature of T1 and the fluid 2 is at temperature T2. Okay. This one is T1, and from T1 to the wall till the let's say dirt, you have the CV resistance RCV, okay. And then from here to the wall you will have the falling resistance, okay. And in the wall you will have the conduction resistance RCD, and again on the outer tube you will again may have the contaminants, therefore you will have the falling resistance, okay. And this one is CV inner tube and falling inner tube, falling outer tube, and then from the falling resistance to the fluid 2 you will have CV again, and then you will get T2 and RCV outer. This is the thermal resistance between these two fluids. Okay. Now let's analyze this thermal resistance. What we get: RCV inner tube is 1 divided by a convective coefficient of inside the inner tube, which is fluid 1, into area, surface area inner tube. Okay. This is the first thing, and then you will have the falling resistance inner, and then you will look for the tables and divide by the inner surface area, and then CD resistance. You will have the thickness of the wall. So if the wall has some thickness T, divided by K, and then the surface area of the wall, and the CV outer tube, you will have 1H outer and the AS outer, and also falling resistance of the outer tube, you will have tables divided by AS outer tube. This is the general thermal resistance network for this tube. If you get the sum of these resistances, you will get the thermal resistance between T1 and the T2. If I write it, R total will be equal to the sum of this one, sum of that one. Okay, so total resistance. And then heat transfer between T1 and the T2 will be T2 minus T1 or T1 minus T2, it doesn't matter, divided by total resistance. And if you make a simple approximation here to understand the picture better, so approximation, simple approximation will be that the wall is very thin, okay. And the second thing is that we can say that the pipes are new, let's say new, and no falling. Okay. And from the first approximation, wall is very thin. From this approximation, we'll get two results. One is that RCD neglected, because if the wall is very thin wall, whatever temperature you have here, T1, that temperature will be also here, T1. Okay. This is the first result, and the second result will be that if the wall is very thin, the surface area of the inner tube will be approximately the same as the surface area of the outer tube, because if it is very thin, then the surface area of the inner tube will be approximately the same as the surface area of the outer tube. This will be the result of this approximation, and then this one will be equal to delta T divided by RCV inner HS. Areas are the same, then this one can be neglected, no, and we don't have it here, and the surface areas becomes almost the same. So R total here becomes CV total. Okay, and if I write it in better form, you will have 1 by H inner area plus 1 by H outer area. And as you can see here, the areas are the same, and the resistance is dominated by inner convection coefficient and outer convection coefficient. If we can look for two extreme cases, H inner much greater than H outer, and H inner much less than H outer. These are the two extreme cases. If H inner is much greater than H outer, okay, or the opposite here, so it means that this one is most probable. It is this one is most probably it is liquid, and this one is the gas. Okay. Therefore, you will have a problem here. The problem is that the gas side will have a lot of resistance. Okay. Gas side will have lots of resistance because 1 by H. If this one is very small, then this one will be large. Okay. Then the gas side will have high resistance. In the high resistance gas side means that you will not have heat transfer from fluid 1 to the fluid 2. So this one will be very hot and it will remain hot, and this one will be cold and it will remain cold. Okay. Therefore, to prevent these two extreme cases, what we will do is that the famous thing that you know, we will add the fins. Okay. This is the famous stuff that we will do. On the tube side, you will have the fins. Okay, this is the result of the thermal resistance network for the fins, and we will now introduce overall heat transfer coefficient. Now I will write Q dot as U into surface area T1 minus T2. Okay, so it is very similar to so Newton's law of cooling, so which says that Q dot is H A T1 minus T2. Okay, so I'm introducing U value here, and I'm introducing AS. Okay, the AS is any AS that I've chosen, and the T1 minus T2 is the difference between 1 and the 2. So what I will do is that I will write the heat transfer as resistance T1 minus T2 by the resistance. That resistance will be 1 by U into AS. Okay, this is the formula that I have introduced, and this is the resistance for my formula. Okay, and this resistance 1 by U into AS should be equal to the resistance, sum of the resistances here. So it will be 1 by inner H in inner surface plus T into K into area wall plus the falling resistance of the inner part divided by surface area inner part, falling resistance of outer part, surface area of the outer part, plus 1 by H outer area S outer. Okay, and here we have all the resistance summed as the U into AS. Okay, now as you can notice here is that overall heat transfer coefficient, if I use my approximations here, then this term can be neglected, this term can be neglected, this term can be neglected. 1 by U AS will be equal to 1 by H inner into area plus 1 by H outer into area. Okay, and if I have AS, if I've chosen AS as the area, it doesn't matter surface area or outer surface area, it will be that 1 by U will be equal to 1 by H inner plus 1 by H outer. Very similar to discussions here. So the overall heat transfer coefficient is dominated by the values of the H inner if it is greater, or H outer if it is greater, if you look at these two extreme cases. Okay, and this is the U value for the heat exchanger, and this U value is called overall heat transfer coefficient here. This is the same U.